So everything in that last video is built upon how we started with the idea of secant line with this average rate of change, which we could also express as this difference quotient. And this is really key here. And all of that links to a secant line between 2 points that are graphed, and we would be finding the slope of that secant line. So that's what the difference quotient does, as well as the average rate of change. Again, average rate of change is just over that interval a to b, and then difference quotient, we just think of having some x coordinate, and then x with a certain distance away with a plus h. So now what we're doing is to move to the idea of a tangent line to get an instantaneous rate of change through a single coordinate. What we can do is take that calculation for the difference quotient, and where we have a coordinate and then maybe something that's a certain distance away, evaluating that as a limit as h approaches 0. So as that distance closes in, what is this rate of change doing? And again, we can't evaluate it at exactly 0 at the beginning, because just from this format, that would throw a 0 into the denominator there, and it would all become undefined. So that's where we need a limit to get this idea of what's happening as we approach 0. So, some notation. So we are talking about the derivative here. Again, there's lots of different ways we can describe a derivative. It relates to the slope of the tangent line. We also call it the instantaneous rate of change. So all of those terms are interchangeable with each other. Depends on what we're really talking about, but the derivative is the short name that we use, but that can apply to finding the slope of a tangent line. It can also apply to applications where we're looking for an instantaneous rate of change. So, our notation. We're going to see some different formats of notation. I'm going to jump into the middle of it actually with this m with the subscript of tan. So the m is relating exactly to what we use for slope, where we use y equals mx plus b. This is just relating directly to slope of the tangent line. This notation we might see pop up, but it won't be very often. Instead, we're really going to focus on these first two forms of notation. So this first one, how I would read it out loud is f prime of x. And really, it's the derivative of f of x. That's what it represents. And reading it out loud, I'll switch between the two. The derivative of f of x, f prime of x. Same exact thing. This next one, we read it just as it is, dy dx. It could also be read as derivative of y with respect to x. And really you could think of these two as a difference of using function notation versus like y equals some function of x notation, but those can also be used interchangeably. So you'll see both come up. We'll have moments in the quarter where we prefer one over the other just for organizing our work, but they all represent the derivative of f of x. So we can do f prime of x, dy dx, and then how we're calculating that for right now in the quarter is with this limit, the limit of our difference quotient. So this is the limit definition of our derivative, of using that difference quotient and evaluating the limit as h approaches 0. As we move through the quarter, we're going to get some shortcuts for these methods, but for this module and this point in the quarter, if you're finding a derivative, you have to use this limit definition, because all the shortcuts we eventually get to use that make life so wonderful all come from this limit definition. So we need to make sure we know how to apply it, so we have these basics of how do we calculate a derivative. So let's see this in action. So for this part of the module, we're focusing on evaluating the derivative at a specific point. So what that means is we're going to be given a value for x. So here we have our function, so this 3x squared minus 4x plus 1, and we want to evaluate f prime of 2. Or we could say that as the derivative of f of x at 2. So we're evaluating this at x equals 2. So getting my limit notation together. So how I could write this is I'm calculating f prime of 2, which would be taking the limit as h approaches 0 of f of, and then where it would be x plus h, we're going to be using 2 plus h minus f of 2 all over h. Now, the process here, you have a few different options for how you want to simplify this. But altogether, the work is going to be included one way or another. You can either include it all in one go, or you can do some side work and kind of piece it together. So, what I mean by that is, let's say I kind of separate off some side work here. First thing, or not even first thing, but one of the things that we'll need is we need to know what f of 2 is. So to find f of 2, we just need to plug into our function. So that'll be 3 times 2 squared minus 4 times 2 plus 1, which that's going to be equal to 5. So you know that where we have f of 2 in our limit definition over there, we can replace that with a 5. What I also need to know is f of 2 plus h, and this is a little messier. So this is the one that I especially like to do the work off to the side to kind of make sure I just have a single expression that I'm going to substitute in. So this is going to be 3 times 2 plus h squared minus 4 times 2 plus h plus 1. And what I want to do is just simplify that down. So first thing I need to do is expand out this 2 plus h squared. So I'm going to have this 3 multiplying, and then 2 plus h times 2 plus h, that's going to give me 4 plus 4h plus h squared. Again, all coming from the multiplication of two binomials using FOILing. Distribute the negative 4 in, so negative 4 times 2 is a negative 8 minus 4h, and I still have that plus 1 at the end there. I'm going to distribute the 3 in. So that's going to give me 12 plus 12h plus 3h squared. Let's see, minus 8 plus a 1, so negative 7 minus 4h. And I'm going to go looking for like terms. So I have a 12 minus a 7. I also have a 12h minus 4h. I'm going to go ahead and throw this into standard form too. So I'll have a 3h squared and then a plus 8h and then a plus 5. Okay, that was all my side work that I need to do for this one. Now that I have that, I have this expression that I can just go and substitute in for f of 2 plus h. So if I go back to my limit definition over here, this is evaluating the limit as h approaches 0. F of 2 plus h can be replaced with the 3h squared plus 8h plus 5, and then minus f of 2, which we found is 5, all divided by h. And now I'm just going to simplify down. So this is the same as the limit as h approaches 0 of 3h squared plus 8h over h. I have a common term of h that can divide out. You can do this either by factoring out an h in the numerator and canceling, or you can just see one of those h's will come out from each of those pieces. So I'm going to have the limit as h approaches 0 of 3h plus 8, which now I can plug in h equals 0 and end up with 8 for my final answer. So the process there. I start with my limit definition of the derivative. I can do side work first to evaluate what I'm plugging in for those function outputs. And then simplifying down, you should get to this spot where you can cancel out an h with the denominator. Basically, we want to get to a point where we can plug in h equals 0. That should be our last step that we're doing here. We're just working with it until we can get to that point where we can plug in 0 for h. And then we should end up with a single number at the end, because what we're getting is that instantaneous rate of change, or the slope of the tangent line. So if I graph this function and I evaluate it at x equals 2, this would be the slope of our tangent line. We should see a pretty steep slope coming through there. Other recommendation for notation as well, that limit notation has to stay throughout that work until we plug in h equals 0. So we're evaluating the limit all through this process until we plug in h equals 0. Okay, one more example here. We're going to find the equation of the tangent line. So with this one, where it's going to differ is this was just finding the derivative. Us finding the equation of the tangent line is finding an equation y equals mx plus b, where our slope relates to the derivative. So we have our function is x squared. We're going to evaluate at x equals 3. So if I want the slope of the tangent line, what I'm going to do is evaluate f prime of 3, or the derivative of our function at x equals 3. That will give me my slope of the tangent line. So to do that, we're taking the limit as h approaches 0, and we'll look at f of 3 plus h minus f of 3 over h. Now that last example, I did it as side work. I'll show you how we can just do it all together in this spot. We just have to be really careful with our steps. So I'm plugging in 3 plus h into my function x squared. So what that would look like is we'll have our 3 plus h, and that's going to be squared, minus, and then our function with plugging 3 in, which would be 3 squared. What we just want to make sure is that we have our first piece that we're plugging in minus the second piece that we're plugging in. We need to make sure those are separated by subtraction in a clear way. And I wrote those too closely together because I still need my limit notation as h approaches 0, and all of that is over h. And now we're just going to simplify. So the limit as h approaches 0, foiling out 3 plus h squared will give us a 9 plus 6h plus h squared. And then we have subtraction of 3 squared, which is 9, all over h. And that'll be equal to the limit as h approaches 0 of h squared plus 6h over h. And then we get to a point where we can cancel out an h. So we'll just have an h plus 6, which means plugging in h equals 0 is that we're going to end up with 6. So that right there is our derivative at x equals 3, which means that's going to be the slope of our tangent line. So where I'm fitting pieces together to get y equals mx plus b, we just found our slope, 6x plus b. Now, to find what b is, we need to plug in a coordinate, and we need to specifically use the coordinate that we were told about where we know x is 3, and when x is equal to 3, our function output is 3 squared, which is 9. So we're going to use this coordinate that we're focusing on. We can't use any x value. We specifically need to use the x value they told us about. So we're going to plug in 3 and 9. So that's going to be 9 equals 6 times 3 plus b. So 9 equals 18 plus b. So b is going to be a negative 9. So an equation of the tangent line, it's going to have a slope of 6 and a y-intercept of negative 9. So for the equation of the tangent line, we go through this process where we use the derivative to find the slope, and then we plug in that coordinate to find our y-intercept.